morning.
Good morning, sir.
Okay, so in the previous class, we discussed about how noise can be estimated, how noise can be removed by using various mean filters. We also discussed about how we can remove uh, periodic type of noise, that is sinusoidal type of noise, by using band reject filters. Now, in this class, let us discuss about how we can perform uh, in fact restoration when there is only blur in the image. Okay, so is our not visible now? Hello, can somebody respond?
Yes, sir.
Okay, okay. So if you remember, the model that we have actually is this. The degraded image is actually with the assumption that the degradation function is linear and shift invariant. Degraded image is convolution of the original image with the impulse response of the degradation function or the system. And impulse response is also called by another name. Can somebody tell me what is the name of impulse response in 2 dimension? What is impulse response in 2 dimension? We have given a different name. What is it?
Point spread function.
Yes, I think point spread function, PSF. Okay, so the case one which we discussed earlier was when there is only noise. So only noise means I am assuming that the point spread function of the uh, camera or the acquisition device is an impulse. I hope you remember. So when I convolve uh, any image f of x comma y with an impulse, I'll get back f of x comma y. So the model was this: f of x comma y is f of x comma y plus eta of x comma y. So this is a model which we have already discussed, and we learned how to estimate noise, and then we learned how to filter that noise by using various filters. If it is salt and pepper type of noise, I can just use a median filter. If it is Gaussian type of noise or Bayesian or anything, I can use different mean filters like arithmetic mean, geometric mean, etc. If I have uh, the noise to be maybe okay, if it is for example periodic type of noise, I can just use band reject filter to remove it. Now the second case what we are discussing today is, I am assuming that blur is the only degradation. So in this model now, I am assuming that there is no noise. Okay, that is the second assumption we do. So what would be the model? G of x comma y is convolution of the image with the blur point spread function h of x comma y. So if you go to the frequency domain, then I'll take Fourier transform on both sides. Right hand side f of x comma y will become f of u comma v. F of u comma v, and convolution becomes multiplication. All of you know about it. So this would be the model now. When I assume only blur, and no noise, this will be the model. Okay, so with this model, now what we need to do is, if I want to find, say, what is required is, I want to find f of uv, and you know f of uv is g of uv divided by h of uv. So it looks as if when the blur is estimated, okay, I can just divide the Fourier transform of the degraded image by the Fourier transform of the estimated blur, and I'll get f of u comma v. So if I take inverse Fourier transform of this, I'll get f of x comma y. Inverse dft, I'll get f of x comma y. And it may not be exactly f, therefore it can be f hat. So this is the situation. Now the question is, who will give me this? Whenever I get an image, nobody will tell me what is a blur in the image. So you need to estimate this degradation function. That is exactly what we are discussing now. Okay. Okay, now I think the slide should be visible to you. So we need to estimate the degradation function. There are three ways of doing it. One way is you estimate by observing the image. Okay, that means you need to closely look at the blurred image, try to okay, estimate the blur based on the observed image. The second is by performing an experiment. Okay, I'll just explain how this experiment can be performed. And the third one is estimation by modeling. Okay, so these are the different methods of estimating a degradation function: by observation, by experimentation, and then by modeling. Okay, so let us take one by one. Now what you need to do is, in the first case, when you want to estimate by image observation, you just take a window in the image. Let me just go to an image. Okay, for example, in this case, okay, this is a blurred image. So what you need to do is, you should just take a small portion here, that means a window here. And in fact, this is not known to me. I will go to the corresponding, this is what is given to me. So you just take a small window here, that's what it means. Okay, so take a window in the image, and where you have to take a window, you cannot take it in the smooth region. For example, if you carefully observe, in this case, this is a smooth region. In the original image, this is a smooth region. So by just taking a window here, I don't get anything, because a smooth region, when it is blurred, what will you get? I have explained this several times. A low pass filter is a blurred, okay, is applied to a smooth image. What will I get when I apply a low pass filter? Smooth region means it is low frequency or almost zero frequency. So what happens? Can somebody? Can somebody chat or speak? If I pass a smooth region through a low pass filter, what will happen? What will be the output? Nikhil Kumar. Nikhil Kumar, unmute yourself and speak.
Yes, sir.
Yeah. When I pass a smooth region through a low pass filter, what will I get? What is a low pass filter according to you?
Sir, which allow only low frequency to pass through
Okay.
it.
Yes, correct. So smooth region means what type of frequencies will exist in that region? Smoothness means there is no variation. So what frequencies you will have there?
So low frequency.
Low frequency. So a low pass filter, low frequency will be passed, correct?
Yes, sir.
Okay, so thank you. So smooth region continues to be smooth. You observe here, whatever smooth you have here, same thing is there after blurring also. So that is why if I take this smooth region, there is no difference between the original image and the blurred image. So there is no use taking the window in the smooth region. Okay, so that the window should be taken in the strong signal content, not in the smooth region. Okay, so what is the strong signal content? When do we say the signal is strong? There should be a sudden variation in the image. So it would be good I take, for example, in this case, you can observe here there is darkness here and there is brightness here. So this is a strong signal content. Suddenly the value is going from very low value to high value. So I need to take such structures here. Okay, that is what is important, because that is where you have to estimate the blur. So take a window, and it can be a simple structure but having strong signal content. So best thing is to go to a corner point or to an edge point and take a small window there. Okay, now then what you need to do is you should now estimate the original image in the window. How I should, okay, this is already known to me. That means the deep blurred image Fourier spectrum is available to me. I will estimate what could be the original value at that particular region. That means I'll take a small region here and just try to see, for example, this is going from dark to white. So the variation is very smooth because of blurring. Actually, in the original image, it is a sharp transition. So what I'll do is I'll try in this small window, I would like to try to estimate the value. For example, this could be very close to say some 10, and this could be very close to say some 100. So in that small region, I'll just estimate, okay, the values. So once I get that estimated value, and just now I showed you the equation for G, I can do it again. Okay, so this is the equation now. What you need to do is I have to estimate H, so H is G by F. So that's exactly what is done here. That is exactly what is done here. So H is G by F. Okay, only difference is it is not the entire G, it is that small window that you have taken. That means the Fourier spectrum in that small window and the Fourier spectrum in the small estimated region. Okay, I hope you understood. So thereby I just find Hs, and in that small region I have determined the blur, and I'll assume that the blur is same all across the image and use that estimate to, in fact, to further do restoration. So this is one way of doing estimation of image degradation by using observation. I repeat, I have to take a small window in the blurred image, and that structure has to be very simple and it should have strong signal content. So best thing is to go to a corner point or to an edge point. Now estimate what could be the original pixel values there and find that spectrum. Divide the Fourier spectrum in that region of the blurred image by the estimate. That will give you the blur in that small region, and assume that the blur is same all across the image. This is the procedure. Okay. The second one is by doing experimentation. Again, let me go back to here. So this is your model. G of x comma y is f of x comma y convolved with h of x comma y. Now what you need to find is h of x comma y. So can somebody tell me what is h of x comma y? What is it? What is the name at least? Somebody means nobody will speak. Jaya Rohit. Jaya Rohit. Unmute yourself.
Sure.
Yeah, what is h of x comma y? What is it actually? Oh, yeah.
Point spread function.
Yes, it is point spread function. And what is this point spread function? Yeah, somebody says degradation function. Yes, correct. So what is this? See, this is the impulse response of the system, correct? Am I correct? Okay. So h of x comma y is the impulse response of the system. So if you want to estimate this, which means you have to estimate, you have to find the impulse response of the system. Now, what is the system? In our case, the system is the camera that I have used to capture the image. So what I'll do is, I will use the same camera and try to find the impulse response. And I already told you what is an impulse in 2 dimension. This is not to Jay Rohit. Rakesh B.
Yes, sir.
What is an impulse in 2 dimension?
Sir, it's sinusoid.
No, it is not an impulse. What is an impulse in 2 dimension? How does an impulse looks in 2 dimension?
Point spread function.
No, that is the impulse response. So I have explained this why it is called point spread function. During that time I have explained what is an impulse. Anybody? What is an impulse? If you want, you can chat. If you cannot speak also. What is an impulse in 2 dimension? Delta, correct. Delta is correct. Nitin says delta function. Yes, impulse, delta, both are correct. In 2 dimension, how does it look? It's a point source of light. Correct. Yeah, correct. Purnima says point source. Okay. So it's a white dot or a point source of light. So finding impulse response of a system means I should take a camera and capture a point source of light. Okay. Take a camera and capture a point source of light. So that is exactly what is explained in this slide. Okay. So estimation by experimentation. Of course, this can be done only if I have the camera with me. I cannot do this for satellite images. All of you know satellite images, the camera is on board the satellite. I only have the images with me in the ground station. So in that case, I cannot use this method. I have to use maybe by using image observation or the third one. So estimation by experimentation cannot be done in satellite imaging. The reason because I don't have the camera with me. The camera is on board the satellite. I only have the images with me. Okay. So find the impulse response means assume that this is an impulse. So you could see that this is an impulse, point source of light. I hope the white dot is visible. Use the camera, capture this. So it means that I am applying an impulse to the system. Whatever output or whatever image that I get will be the impulse response. Okay. So this is by experimentation. That means use the camera, capture the point source of light. Whatever image you get or whatever output you get from this will be the point spread function. Obviously, whenever the camera is introducing blur, you know, white source of light gets spread like this. I explained this in the previous class. Okay. So this is by observation, sorry, experimentation. And third one is interesting. This is by modeling. Okay. So of course we don't give explanation for these equations here, but what you mean by modeling is depending on what type of blur it is. For example, if it is due to some atmospheric okay variations, the atmosphere in the model for this atmospheric type of blur is shown by researchers with this equation: e to the power of minus k u square plus v square to the power of 5 by 6. Okay, so you don't need to derive this. Okay, this by doing some research they have developed a model for it, and by using this model I can I can just estimate the blur. The only thing that I need is what are the different values of constants. Okay, so for different value of constants you can see that the blurring effect is different, as you can observe here. So I need to model the blur by using some equation like this. Okay, the best example that I can give is the motion blur. Um, all of you know, whenever there is a relative motion between the camera and the scene. For example, I am sitting on a vehicle and capturing a still uh, frame, or vehicle is moving, a still camera is capturing a moving vehicle. So you have relative motion between camera and the scene. So in such cases, what happens is, in such cases, what happens is, uh, you are capturing the image where the image pixels are shifted. Okay, so that means your original image gets shifted because of motion, as you can see. So there is a shift in the image because there is a relative motion. Now, why motion blur occurs? Because your camera has got some exposure time. All of you know, that is why they say when you are capturing the images, they'll say don't move, stay still till the camera completely captures or the image is exposed. Okay, so there is an exposure time. Of course, present day cameras, the exposure time is very less. That is why a very little blur you can expect when images are captured. But earlier cameras, you know, you have to really be still till the complete exposure happens. It used to take more time to okay, capture the image. Okay, so during this exposure time, whatever changes that happens in the image, okay, will be averaged. So that is the reason they say don't move. If I don't move, then my x naught of t will be equal to 0, y naught of t will be equal to 0. That means there is no shift in the image. Therefore, the integration of that, you would definitely get the image without any blur. But since there is a shift in the image, during the exposure time, this shift gets averaged, and because of that, you get motion blur. Observe here. Okay, I hope you can appreciate the blur along this direction. This is because of the motion. Of course, here intentionally the book is moved and image is captured. Just to capture the image, what they have done is they have taken the uh, textbook image itself. In fact, textbook is kept on the table, image is captured, and then the book is shifted and captured. So you can see that motion blur here. I hope you can actually appreciate the motion blur in this second image. So during the exposure time, whatever changes that happens in the image, that is going to be averaged. That is why particularly when there is okay, movement. For example, if you are trying to capture image of a maybe a football game, you know, people are moving very fast. So because of this motion, no, whenever you capture the image, you may not get the image to be clear. It would be definitely blurred. Okay, so exposure time is very important. Lesser this exposure time, lesser will be the blur. But there is definitely some finite value of exposure time for any camera. Within that exposure time, whatever that happens is going, the image is going to be averaged, and that is why the image looks blurred. So this is modeling. What we have modeled here, the model that we have done here is the motion that you are talking about is a planar motion. Planar motion means there is a movement towards x direction, there is a movement towards y direction. Okay, so this is a planar movement. So in this planar motion, why planar motion? Because you know there is no movement in the z direction. See, for example, not only that image is shifting by okay, to x and y direction. Suppose if the image is also moving away from the camera or moving towards the camera, we also have z direction movement. So we are not assuming that here in this model. We are only assuming that the image moves in the, in fact, it is not even rotating, it is just moving towards okay, in x and y direction. Okay, so I hope it's clear. Now let us take the Fourier transform of this. Okay, this is a model. The degraded image that you get is modeled by using this equation. Okay, integration, because the variation in the brightness is going to average, so that is why you have to integrate. T is the exposure time, x0 and y0 are the shift in the image. Okay. So if you take the Fourier transform of this, all of you know what property is used here. Can somebody tell me? What property of Fourier transform is used here? Somebody should respond, otherwise I'll take names. Ravi M. Ravi M. Ravi M is absent. Sannidhi Jain. Sannidhi Jain. Absent. Sri Gauri Ganesh. Sri Gauri Ganesh. Yeah, either you have to unmute or you have to speak. Sannidhi Jain says unable to unmute. Why don't you at least chat if you cannot unmute? What is the property I'm using here? Anybody? Yeah, time shift. Okay, of course here it is, I cannot call it as time shift, it is a shift in the spatial domain actually, but you are right, almost right. Yes, okay. So any shift, okay, in the image, when I take the corresponding Fourier transform spectrum, all of you know what happens. The original spectrum gets multiplied with e to the power of some value which is proportional to the shift. Okay, this is one of the property of Fourier transform. All of you have learnt time shift in one dimension and of course shift in the spatial domain in two dimension. Both of them are almost same. Okay, so a shifted signal, the corresponding Fourier transform will be the original spectrum multiplied with exponential with the okay term proportional to the shift. Okay, so it will be f of uv into this. Now when I have to apply integration, and you know f of uv is a constant now, so it has come out. So this will be your in fact the blur transfer function. Observe the equation here. G is equal to f into capital H. That is what we have seen. So whatever you see here within this integration, this entire term, this is h of uv, that is the blur transfer function. Okay. Now this blur transfer function is a function of your x0 and y0, and it also depends on u and v, you can see. So if you estimate the shift, you have estimated the blur transfer function. So that is how I can apply this model. So let us see an example here. This is a original image. What is done is using this equation here, taking the exposure time to be equal to 1, as you can see, and the shift is taken to be simple uniform shift, something like a times t plus b times t, like that. So the value of a and b are taken to be some 0.1. Okay, so with these values, what you see here is a motion blurred image. Okay, so let me repeat. We are into the third method of estimating the blur transfer function, which is estimation by modeling. you have to develop a mathematical model, and we are taking an example as motion blur. So the meaning of uh, capturing a motion blurred image is you are exposing a shifted version of the image over a specific exposure time t, which is the model. If I assume the motion to be simple planar motion, that means movement only in x and y direction, you are going to average the image over that particular region. That is why this integration during the period exposure time t. Now using the uh, shift property or shift in the spatial domain property of a Fourier transform, I will obtain this. So this will be your blur transfer function, which depends on the shift x naught and y naught. If I assume the shift to be simple uniform motion, like something like linear motion, a times t and maybe b times t, like that, then by using different values of a and b, I know what is the amount of blur. Sorry, okay, I have the blurred image here. This is how I can estimate by just using modeling. Okay, so the only requirement is what is the model that you use. That depends again on the motion that has happened. If there is a complex motion like rotation or movement in the z direction, this model cannot work. You have to modify the model. Okay, so what next? What we did, we have estimated the blur now. Okay, and assuming that there is no noise. But if there is also noise, the model looks like this. All of us have understood this. G is f into h plus n. This is when noise and blur, both of them are there. When blur is not there, that means this term is missing. It is only f plus n. When noise is not there, it is just f into h. But when both of them are there, the model will be this. Now, the meaning of restoration means I should pass this type of image through an inverse filter, correct? That is a meaning. That means I had to, whatever that has happened here, the opposite of it should be done. That means I should pass it through an inverse filter. So passing it through an inverse filter means this has to be divided by h of uv. Multiplying it of h of uv means you are blurring it. Dividing this by h of u means you are passing it through an inverse filter. That means 1 over h of uv is the inverse of h of uv. So it is g by h. Okay, this is g by h. Now if you divide this whole thing by h, if you divide this whole thing by h cancels, so I get f of uv. Second term will be n by h. So the problem lies in this equation. Sorry. Is the slide visible? Is the slide visible?
Yes, sir.
Okay. So the problem lies in this equation. What is the problem? First of all, noise is unknown. Okay, we have learned how to estimate it, but that is only an approximation. Okay, so noise is unknown. The second one is, even though I estimate the blur, blur means it is usually low pass filter. Low pass in nature means at low frequencies the magnitude will be 1, whereas when I go to high frequencies the magnitude decreases. All of you know how the low pass filter response looks like. Okay, so at high frequencies the value will be 0 or it will be small. So you are dividing a term by 0, and anything divided by 0, this is going to be in fact exaggerated. That means your noise is going to be increased. So this is a problem. That means when I go to higher frequencies, the value of the blur transfer function will be 0 or it will be very small. Dividing noise by very small value means noise is going to get exaggerated or increased. So this is actually a problem. Now what is the solution for it? The solution is simple. what you do is don't go up to that high frequency. That means when you are dividing, go up to a frequency where h of uv is equal to almost equal to unity or very close to unity. Don't go to the smaller values. That means let me just explain this probably with the one note. So what I meant here is a low pass filter, simple low pass filter has got this type of response, all of you know. So in this region, what you observed is your h of f or the blur transfer function is very close to 0. In fact, here it is almost equal to 0. So if I divide by this function, definitely n divided by h in this region will be very high. This is the problem we are facing now. So the noise is going to be increased. So what you do here is don't divide the values in this region. Just restrict yourself to this region. That's exactly what is explained. So restrict yourself to frequency around the origin. Okay, that means don't go to the region where this h is becoming very small. So by doing that, an example is given, I think. Let me just show you that example. Okay, so look at the example here. So here, this is actually restoring with the full equation. That means with dividing. As you can see, restoration has actually spoiled the data. This is by using full filter. But this is by using h that is cut off outside the radius of 40. Okay. This is outside the radius of 70. This is outside the radius of 85. So what you notice here is these two look better. So you can just decide h to be the radius to be around 40 or maybe around 70 and just try to restore. Okay. Full filter, you have the problem. In fact, radius about 85 also has a problem. So something around 70 looks to be better. So just try to adaptively modify this radius and try to estimate it. Okay. So that is how I can avoid the problem of inverse filtering. Okay. Particularly limiting in the frequency around the origin. Okay, I think this needs some explanation in detail called minimum mean square error filtering. So I would like to take up this topic in the next class.